The Department of Materials Design and Innovation is a brand new and transformative department that is focused on ways to use data science and materials informatics to train and educate materials scientists for both research and education. The process to create this department involved finding individuals who not only were talented in their own respective fields, but have the ability to work across disciplines in new and exciting ways. Diversity is so important to this department for both its intellectual breadth and the need for having individuals who can address a broad range of social problems where material science can have a great impact. An important objective of our department is the ability to translate material science or fundamental material science research and accelerate solutions that industry can use. One such example of that is our partnership with the Toyota Research Institute, where we bring teams of faculty together with students applying a broad range of experimental and data science tools to discover new materials for the needs of solving problems to the industrial community.
This department is unique because of its marriage of data science methods with material science questions. We're interested in how do you find new materials, how do you find materials that can be substituted for materials that are difficult to obtain or maybe harmful to the environment. And we're using data science methods in order to explore those questions and discover new answers. My research has been at the intersection of quantitative methods and discipline-specific questions. And that's what materials design and innovation is really all about, bringing data science methods to bear on material science questions. So it's a natural fit.
My research is at the nexus of computational physics, computer science, and material science. I'm currently designing heterogeneous microstructure for next-generation solid oxide fuel cells, lithium-ion batteries, and organic solar cells. The goal for my research group is to accelerate the way we design heterogeneous microstructure. I hope my research will change the way we design materials in future for next-generation batteries, but also for solutions to sustain energy in our household, and will lead to significant changes for developing countries.
My research is growing two-dimensional materials, mainly graphene and transition metal dichalcogenides, and growing vertically stacked heterostructures of these materials. And people usually study these with Raman spectroscopy, but we're trying to also use terahertz spectroscopy because that corresponds in frequency and therefore in energy to the very low frequency end of the Raman spectrum. So we would be looking at similar energies and similar phenomena, but using two different spectroscopic methods.
My research will generate a transformative understanding on the structural mechanical properties of soft materials. We are questioning the fundamental knowledge behind the soft material elasticity. This knowledge, we believe, will enable us to develop soft, reliable networks, which will have a tremendous impact on both biomedical as well as tribological societies. These materials can be synthesized or they can be naturally occurring in nature. Hydrogels, which are commonly found in eye contact lenses, are examples of synthetic networks, whereas the cell and tissue networks are naturally occurring materials. Being at the Department of Materials Design and Innovation has already opened up several possibilities in my research. This not only reduces the concept to the development timeline, but I believe that this will also have a tremendous impact in industry-academic relationships.
What we're trying to do is at the forefront of bringing data science research methods into the education program so that students naturally move from material science questions and using data science methods in order to explore answers to those questions.
MDI is unique in many ways. One way is the way we teach our students. For example, I am co-teaching kinetics of materials, where I provide students detailed theoretical background, and another professor is providing them with detailed experimental background. I think this is a very unique aspect of the way we teach our students.
I hope this department can help change the perspective a little bit about how data is used in physical sciences, rather than just digging through huge amounts of data, to use sparse amounts of data to guide the direction of research.
We have a broad range of students, skill sets, and faculty doing exciting research at the forefront in a broad range of innovative fields. We see this as the template for a new approach of how we produce a next generation of material scientists that can impact not just technical areas in material science, but have a positive impact on social well-being to the community.